All right, section 4.4, we're going to be looking at the fundamental theorem of calculus. So anytime in mathematics where you see the fundamental, something about being fundamental, means it's really important. So there's a fundamental theorem of counting. Comes up in one of my classes. Came about a month ago. There's fundamental theorem of algebra, right? And today we're going to do the fundamental theorem of calculus for us today. And the fundamental theorem of calculus actually is where we have been building up to with some of the notation that we have seen. If f is continuous on AB, and capital F is the antiderivative of the lowercase f, then the antiderivative from a to b of f of x dx is capital F of b minus capital F of a.
Are we going to memorize these?
Yes. This is one of them. This is short. This is the shortest thing I've asked you to memorize so far. Yes.
You're right.
It is, right? It's one sentence. I think you can handle it. I don't think you can. I know you can.
I don't know if I can.
You can. Okay, so what is this saying? Well, this is saying we're going to use those antiderivative rules that you guys just took a gateway on, right? And we're going to evaluate the antiderivative at the capital F of x at the beginning point, the top value, b, and then we're going to evaluate it at the lower point, a, and we're going to subtract the difference. Okay? So I'd like to show you what that looks like in terms of a problem. We're going to look at a technology component here in a moment as you saw me setting that up. But first, let's actually look at what this looks like in terms of actually computing it by hand a little bit. So what we're going to do is, much like you do on the gateway, you're going to take that negative 3x plus 4, and you're going to find the antiderivative. So tell me what you get. Now what? And plus c. Okay, so, well, I won't spoil the fun just yet. Okay, so here's what we have so far. That's what you know how to do. You've known how to do that now for several class periods. What we're going to do at the end is we're going to put a vertical bar. We're going to put the lower limit on bottom, the upper limit on top. So it very much sort of looks like it's transferring from the beginning of the statement to the end of the statement. And these are evaluation bars. Okay? So we're going to evaluate this statement at the point 5, or at the x value 5. So 3 times 5 squared over 2 plus 4 times 5 plus c. And then we're going to subtract, and we're going to evaluate that also at the value 2. So negative 3 times 2 squared over 2 plus 4 times 2 plus c. Okay, so the first thing that I want you to notice here is what happens to the c's.
Bye-bye.
They go away. So here's the cool fun thing that I almost spoiled before. When you're doing definite integrals with the a and the b at the top, there's no need to put plus c's, because they're always going to subtract out. If you feel like that's going to make you forget to do them in the other places, put them all the time, it's fine. But there's absolutely no need for them to be there, because they're always going to cancel each other out when we do this, okay? So it would have been perfectly fine for us to have not had it here and done it from that perspective. All right, so after this, it's a matter of putting in your calculator, calculating it in your head, whatever you would like to do, and you're going to come up with a couple of values, subtract them. It ends up giving you negative 19.5. So I'd like to use this same one and to show you a couple cool things that you can do with your calculator. You ready? I'm probably going to have to borrow somebody's calculator because there's 2 different versions of these that are going on out there, and I don't think I need that on actually. This is what I wanted to do. And it looks a little bit different depending on your version. Time. Is it A, is it B? Do you guys remember?
Just try both and see what happens.
Our technology across campus is not uniform.
It's A.
It's B. Okay.
But it said A.
Well, but it says B now. And did A work and then I turned it off and it did B?
Yeah.
I see what you're saying. It was actually registering. Okay. So you're going to help me remember next time that it's A, right?
Make a sticky note.
Make a sticky note. I should put a sticky note in every classroom. Okay, let's try it again. Okay, I'm going to show you a couple of different things. First thing I want you to do is to put the regular equation that we were given inside of y equals, okay? So we're going to put in what did we have? Negative 3x plus 4. Okay, and you're going to exit out of the screen to a regular screen. Do you remember when we explored how to do derivatives on the calculator? It's in the same place. So we're going to hit math, and it's actually number 9 down here. It says FNINT. It's function integration. All right, so when I hit enter here, mine actually looks like FNINT. Whose looks, oh, that's not right. I hit the wrong one. Let's try that again. Okay, whose looks different than that? Okay, I'm going to borrow yours if you don't mind. Thank you. Okay, so if yours doesn't look like that, it probably looks like this. I think if I do, what was it that I did the last time and it worked in my other classroom? I don't know.
You could like zoom in on it.
Let's try zooming in. That'll probably work. So let me use this one first. That'll work. Okay. If you have this version, I'll come back to my version in just a second. If you have this one, your lower limit and your upper limit, it looks just like the actual function that you're given with the antiderivative notation and everything in the problem. So you go 2, you go 5. Technically, you could type the equation in there, but we stored it in y1 because it makes it a little bit cleaner, I think. So I'm going to put vars, y vars function y1 in there, but you could type it all out in there. And this is the derivative with respect to x. Okay? So this is going to calculate for us the exact value. There's the negative 19.5 popping up.
That's cheating.
Okay, well, you have to show it to me anyway. So it is verification at best. Yeah, Nick.
I don't remember if I said this before. You can use alpha trace to get directly to your y's too. You said run through bars mostly. Alpha trace.
Oh, I wonder if that works in my calculator. We'll have to see. Okay, if you've got this one, let me show you what it looks like. Oh my goodness. That magnification, you can see all of the specs. Oh, that's not good. It's like having a magnifying glass on something. Okay. So the way that this one sets up, if you've got this version like I do, is that you have to tell it your function. So you tell it that your function is y1. Yeah, it only works on yours. If you've got the version that I showed you before, that alpha trace will work. Mine doesn't do that. Okay, so there's our value, y1. You have to tell it that your variable is x. That comes next, so y1 comma x. You put a comma to the lower limit and a comma in the upper limit, and then you press enter. I should have given you your backup, sorry. Thank you so much. Okay, so that's good. You can use it to verify, but I want to show you something really fun. You ready? Okay. I want you to make your window go just a little bit further out than 2 to 5. So I'm just going to go from 0 to 10. Okay, this is an equation that's a line, right? It's negative 3x plus 5. So since it's, was it plus 5, plus 4? What do we have? Plus 4. So it's going to start above the y-axis at 4. So I'm going to make my y minimum 0 because that's plenty sufficient. What does my y maximum need to be? Oh, this is a decreasing graph actually. So I don't want my y minimum. Let's just do negative 10 to 10, see if it's okay. I don't want to think about it too much. Okay, does that look all right? Okay, so what we're going to do is we're going to actually, well, I want to go to 0 to 5, but I think I've got it out there far enough. 2, 3, 4, almost. Let my window go just a little bit lower to negative 10, make negative 15. Okay, I want to find the antiderivative, same thing in this screen, but I want it to go from 2 to 5. If you go underneath the calc menu there, right underneath trace where it says CALC, so you hit the second trace menu like that, you have all these options, and the one that is actually looking like what we're doing is number 7. Y'all see that? We're going to select option number 7. It asks you on your screen lower limit. Well, our lower limit's 2. And press enter. Upper limit, our upper limit is 5. And we press enter. And it shades it in.
That's cool.
It's cool, right? You can see that you've got the area there. You can see where the area is negative. So antiderivatives actually find what we would consider net area. So area above the curve is considered positive area. Area below the curve is considered negative area. So the reason this one is negative is because it's predominantly, in fact, only on this one below the x-axis. Okay, so you have ways to verify any of these definite integrals if you wish to. All right. There's one other thing you can do, is if you have already found your antiderivative, let's put it in y2 just so that I don't lose this y1 in case I should need it for some reason. You found it as negative 3x squared, or like this would actually even verify for you that your antiderivative is correct. Negative 3x squared over 2, and then plus 4x. Everybody good so far? And over here in regular screen, you can do vars. It'd be y2, because I put it in y2, of 5 minus vars y2 of 2. And I should get the same thing as well. That's a third option. You've got 3 ways of verifying that you have the right solution. All right, what do you think? Cool technology stuff, right? None of it's absolutely crucially necessary, but if you have your calculator with you, you're going to be happier. Agreed? You are. You're going to be happier with that answer, with that ability. So we're going to switch back to our regular screen, and we're going to move on to the next one. Okay. So on number 2, we have an antiderivative from 0 to pi of 1 plus sine x dx. So I want to focus on this one on what's the minimum work that I expect to see from you now that you know that you've got the calculator who can calculate it without doing any work, right? What do I need to see from you? Because actually, if you wanted to do your web assignment, you want to do it really fast, you could. Truth? You could. It's not going to help you in the long run because you're going to have a test and it's not going to work there. So what do I want to see? Well, I want to see the antiderivative first. So what's the antiderivative of 1 plus sine x? X minus cosine x. Is everybody good with that? Awesome. And we're going to draw our bar and do a 0 to pi. Okay? 2 options. You can write it like we did last time where you're actually putting the value pi in. Pi minus cosine pi. And then minus 0 minus cosine of 0. So that's definitely an option. However, I will be okay with you putting that that's capital F of pi minus capital F of 0. Either of those options I'm okay with. Okay? Because at that point, you're going to probably use the calculator in most cases to find the exact value anyway. Make sense? So on this one, we're going to attempt to use the calculator. We're going to find that it's going to give us an ugly decimal, and we're going to be pushed back into doing it by hand. But in most cases, we will get a value that's just fine. Here, when we try to do this, we have the pi at the beginning. Well, actually, let me just use your calculator. If you attempt to do this, these are zeros. This is 0, and the cosine of 0 is 1. So that one's not actually 0. I was about to say we had zeros at the end. But if you put this into your calculator, it's going to give you a value that looks like, of all of it, it's going to give you a 5.1415. Bunches of stuff like this. That's what it's going to give you. Did it not do that, Nick? For the whole thing? Double check. Did it? Okay, Lainey says it did on hers. I think it should. That's an irrational number. Hopefully you see that somehow pi is embedded in that answer. The decimal expansion at the end looks like pi, doesn't it? 0.14159. That's a pi expansion. So there's a reason for that. But at the point when it gets to this as an approximation, I would expect you to be able to go back and look and try and figure out what the exact value is. So the pi at the beginning is just pi. Cosine of pi is actually 1. And then here I have a double negative, so that's a positive now.
Isn't the cosine of pi negative 1?
Thank you. I left my negative out. Yes, negative 1. And then I have that double negative giving me a positive, and then the cosine of 0 is 1, which we made a mention of before. Negative is a 1 here, so this is actually pi plus 2. And hopefully as you look at that 5.14159, you say, oh yeah, that is pi plus 2, right? It's just 2 more than pi. So this would be our exact answer that we would be looking for, and we do have to do a little bit of actual work that the calculator is not going to support us in very well. Okay, trig functions aside, most of the rest of them work a little nicer. All right, so we already encountered, yes, Nick?
Sorry, I have to make sure, because if I use this in the future, and this gives me the wrong answer, I can know why. What I'm doing exactly is it shows on his board
Let me look at it.
It's not a different job. I think I realized what I did.
See it?
Yeah, I don't know.
Okay, it's always data entry, so I was just gonna find your data
Yeah.
entry. Okay, it happens to all of us. Okay. So, Alyssa did not like the fact that she's got to memorize this one, right? She's going to, just like all of you are going to memorize this one. You're also going to memorize this one. You get 2 for this one. I know. This one's still very short.
Is that all you have to memorize?
That is all you have to memorize for the test, those 2. And at least one of them will show up on the test. Okay?
Oh,
Will they be worth a lot of
they're
points?
Well, they always tend to be worth, like 6 or 7, like in that ballpark, right?
Make it half the way to the test. So
You think if I make it halfway to the test, will you really do it?
I think that's a terrible idea.
It's tempting. I don't think we're going to, but it's very tempting.
That's a terrible
I think
idea.
you should follow that, Tim.
Alyssa doesn't.
All right,
work.
second fundamental theorem of calculus says the following. If you have a continuous function, AB, notice that matches the other one's beginning as well, right? That's the same. And your capital F of x is equal to the antiderivative from a to x of f of t dt. Then d dx of the antiderivative from a to x of f of t dt is f of x. We'll talk about what it means. In a nutshell, this is saying that if you take the derivative of the antiderivative, you get back where you started.
It's a really
wow.
complicated way.
It looks complicated, but that's really what it's saying. There's a little bit of a nuance to that we're going to see happen in actual problems. It's not quite that straightforward, but it's basically what it says, right? If you multiply by 7 and then you divide by 7, what happens? You didn't change it, right? If you take the antiderivative and then you take the derivative, nothing happens. I do want you to notice a couple of things that are sort of specific to this definition. The number on the bottom is actually a constant. Okay, and it doesn't matter what that constant is. So a can be any number on bottom and this will work. And the value on top is the variable x. Okay, so we don't have a constant at the bottom and a constant in the top that we're working with. Constant on bottom, variable on top. Also notice that something changes, right? The thing that changes is that originally inside the variable was t, and when we're done with all of this, my variable is x. All right, so that's also a slight change that happens as we go through the process. So let me show you how it really works so that you can actually see that working. So you'll notice that the directions, be very, very aware of what the directions tell you. The directions say to find the derivative f prime of x, right? Okay, but then they give you this antiderivative to start with. Okay, so it's not going to be just the t plus 2 or turning it into x plus 2 on the inside. It's not quite that straightforward. But what I want to do with you is actually the whole process of let's find the antiderivative and let's find the derivative and let's see how this process up here with the second fundamental theorem actually plays out. Okay? So I want to show you the relationship with this particular example. So the first thing we're going to actually do is to do this process. So what is the antiderivative of t plus 2?
T squared over 2 plus 2t.
Fabulous. Okay, and we don't need the plus c, right? Right, we don't need the plus c. Yeah, okay, sorry, just checking on something. Our vertical bar at the end actually includes something that's not a number. It's sine x on top, and then it's 0 on the bottom. Okay, so far? So then we're going to evaluate the sine x, and we're going to evaluate it 0. So we're going to put sine x in here. So now I have sine of x squared over 2, or you could put the 1/2 in front if you prefer. And then we have 2 times sine of x, and then I have minus 0, right? I have 0 squared over 2 minus sine of 0. Sorry, 2 sine of 0, but it's still the same. And in this particular one, this piece equals 0, and this piece equals 0. I'm putting it into this piece.
You're putting it in.
Oh, I'm sorry. I see what you're saying. You're right. You're right. I'm so sorry. The zooming in, zooming out thing. I'm going to blame that as long as I can. So, sorry. And I still didn't replace it. How about that? It's still 0. Okay. So at this point, what I have actually found is I've found capital F of t here, and then this is capital F of x because my variable changed to x. All right, so far so good? With all the corrections that you guys are helping me make along the way. So I just have, I'll put the 1/2 in front because I like it a little bit better there. This is sine squared of x plus 2 sine of x.
So it's pretty much just.
We're not done, so hold tight to your so. Okay, so far we have capital F of x, but we are supposed to find the derivative, right? So I want the derivative of this capital F of x, which would become lowercase f of x. I know all my symbols are all messing things up at this point. But I want the derivative of this. Actually, I think I'm just going to write that out. Okay, we're doing this one longhand, and I'm going to show you what we can use the second fundamental theorem for. So what is the derivative of 1/2 sine squared of x? 1/2 stays. What do we do with my sine squared?
Do
The chain rule. Okay, so the 2 comes down. I rewrite sine x, which would be sine to the 1 now, right? And then the derivative of sine x is cosine x. And then over here, I have a 2. What's the derivative of sine? Cosine. Is everybody good so far? So here's what I want to show you. This cosine of x is sort of somehow been introduced into the situation, correct? Wasn't there originally? And in a very real sense, well, these two cancel out, right? So this is sine x. And the plus 2, if I pull the cosine of x because it's factorable out to the back, it would look like that. But where in the world did sine x plus 2 come from? It came from this, where the t is being replaced by sine x. You see that? If I replace t with sine x, I have the highlighted part in yellow as a substitution. But because sine of x is not just x, but it's a function with its own properties, right? The derivative of the sine of x ends up being multiplied at the end. So does everybody have what they want of this written down? Because I'm about to delete it and show you what you could do instead. Okay? So what the second fundamental theorem allows us to do is it allows us to take, whoops, I meant to say cut there, this, replace it with that upper limit, which was sine x, and then take the derivative of that upper limit sine x, which is cosine of x. And the reason it does, or how you can see that happening here, is that this says I'm going to take the derivative with respect to x. Here's that x. But it's with a dt on the end, so I have to have the derivative, right? The derivative of the variable x. That's that upper function multiplied at the end by it. So the only thing that this is, only work, I should say, that's actually going on here is this. It's the t plus 2 with the upper limit substituted in. And then we have it times the derivative of that upper limit sine x, because it wasn't just x.
So if we just showed that.
That is all you need to show. We can multiply it out potentially, sine x, cosine x, plus 2 cosine x.
But do we need to?
Yeah, we're going to write it that way. So yes, we'll clean it up anyway, because there's no reason not to. That's it. So all the work that I did to show you that this is what would happen, it will always happen that way. Now there's a nuance happening in number 4 to this. How is 4 different? And I don't mean because it's t squared instead of t. That's completely irrelevant. How is this one different than the previous?
There's minus x. And it's got x on the bottom too.
So say that a little bit louder, Callie. Alyssa
That's a
said too.
variable on the bottom.
There's a variable on the bottom, okay? So notice here, I've got a variable in both these locations, and I talked about the fact that it's actually really important that there is a constant down here, right? We talked about that. We need it to have a constant down there for this to work. So what we're actually going to do is we're actually going to involve one of the previous theorems that we had. I think it was back in section 3, where we're going to split this into two separate integrals, okay? So we're actually going to split this into two separate integrals. And the idea is that somewhere in between x and 3 minus, was it 3 minus x on top? There's some constant. And it really doesn't matter what the constant is. You can pick your favorite number and put it in between. I'm just going to put 0 because, 0 is nice. But there's some number that's sandwiched in between these values. Agreed? Sure, there is. They're not the same value, so there's something in between them. So there's a number in between. If you want to leave it really arbitrary and write the letter a, you could do that too. And what we're going to do is we're going to break this apart to go from x to a. I'll fill it in a second. And then from a to x. And we had this theorem before where we said, hey, look, if it's the value in between, like a is less than b is less than c, we can break apart the integral. We can go from a to b and then from b to c instead of going all the way from a to c. Right? That's what we're doing. Instead of going from x to 3 minus x, we're going from x to 0 and then 0 to x. We're just breaking apart our interval. So far, so good? Oh, sorry. I'm getting so excited. I'm ahead of myself all day today. I'm so sorry.
I get it. It's okay.
It's okay. You guys are really good at catching my mistakes. This would be really bad if you didn't. Okay. Now, our limit of integration, not our limit of integration, but our function, t squared plus 4 dt, and t squared plus 4 dt, go right in there. This piece right here is good to go. Constant on bottom, variable on top, ready. This piece is not good to go. What's wrong with it?
You need a flippy flip.
I need to flip it upside down, right? I need the constant on bottom and I need the variable on top, and we had a property that allowed us to flip it. Do you remember how it changes it if it flips?
Make it negative.
Put a negative in front. So we are in fact going to switch this where we'll have a negative in front, and then it will go from a or whatever number you like all the way up to x of t squared plus 4 dt plus, and this one goes from a up to, or whatever you number want, 3 minus x of t squared plus 4 dt. Okay, everybody good with that? Okay, this one looks, with the exception of the negative in front, but the integral part of it looks exactly like the one that we had before, right? Like the definition here. It actually matches up, it mirrors up the definition perfectly. We have a number on bottom, we have just simple x on top, we have a function with t inside, dt, it looks just like it. This one has that upper limit, the second one has that upper limit where it's not just x involved, so it's more like the previous one we did with the sine x on top. We're going to have to make sure at the end that we multiply by the derivative of the 3 minus x. It's not a very complicated derivative, but we need to make sure that we do it. Okay? So as we're looking at this, this is the function f of x that's been given to us. We are taking the derivative. So taking the derivative means that I'm eliminating the fact that I've got an antiderivative. I'm taking the x and I'm putting it in place of the t. So I have x squared plus 4. This piece becomes this piece. Over here, the t squared gets replaced with 3 minus x. There's addition in between. Oh, there's a negative at the front. I don't want to lose that negative. Sorry about that. Oh, for heaven's sake. There we go. So we're going to take that t squared. So now it's 3 minus x squared plus 4. But I have to take all of that, which is substituting 3 minus x, and I need to multiply it by the derivative of 3 minus x, which is negative 1. If it would help you to think about it every time, you could. You could say, I always multiply by the derivative of the exponent, or not the exponent, but the upper limit. Okay, well, the derivative of x is 1. There it is. So if it helps you to have it in both places to remind yourself to do it, then do that. We're definitely going to clean this up. This is all just polynomial simplification, algebra stuff. So we have negative x squared minus 4. Over here, the negative comes through. So I'm going to put the negative in the front for the moment. And then I have 9 minus 6x plus x squared plus 4, all of it multiplied by the negative. And I just moved this negative to attach it to this positive here in front. We'll distribute that negative through. So here's negative x squared minus 4 minus 9 plus 6x minus x squared minus 4. And let's combine some like terms. Negative x squared. So that's negative 2x squared. How many x's do I have? Just the 6x. And then I have negative 4, negative 9, and negative 4. Negative 17. All right. Okay. All right. A couple more things in this section that we're going to look at. This problem is not different. It's just given to you differently. Sometimes they will ask questions in different ways, but it's the same question. This wants us to find the area of the region bounded by y equal x squared, x equal 2 in the x-axis. So in order to get an image and an equation, not an equation, but an expression with the antiderivatives and everything, we need to actually draw the picture. You can use your calculator for support if you need to, depending on the functions that are given. And you're going to try and figure out what is the area you're trying to find from a graph. So on this one, I want the graph of x, hang on just a second, y equal x squared. So what does that graph look like? That's a parabola. So you have an image that looks something like this. That's a pretty good parabola right there. And then it's supposed to be bounded by x equal to 2. So x equal to 2 is a vertical line. So over here at 1, 2, we have a vertical line coming through. Something like this. I'll shift it. And it says the x-axis. So the x-axis would be on the bottom, right? So let me actually do it in red just to differentiate it since I've already got a black down there. So it's got to be bounded between the curve, the dotted black line, and the dotted red line, and it's that sort of almost triangular-ish shape happening there, right? So the image that I'm finding the area of is right here. Almost as good as the calculator shading it in, right? Almost. So what is this antiderivative? Well, the function's x squared, right? And then I need to think about my limits on x. Where does my shading start and where does it end in terms of the x variables? 0 to 2. Okay? So the calculation we're about to do is not the hard part, right? And I don't even know that necessarily that the graph is the hard part, but it is more complicated. I have to make sure I get the graph set up and the shading done properly, otherwise I'm not going to get the right answer here in a minute. So we start with the setup, we start with the graph, we start with shading it in the appropriate places, and then we're going to find the antiderivative. So what's the antiderivative of x squared? X cubed over 3. And then we're going to put our evaluation from 2 to 0. A lot of times, though not all the times, when we plug 0 into things, it disappears. This is an example of that. So I have 2 cubed over 3 minus 0 cubed over 3. This is 0 at the end, right? What's 2 cubed? 8. This is 8/3. And that area is 8/3. And if you wanted to confirm it with your calculator, you certainly could. There's one last thing in this section, and it's actually kind of interesting. It talks about average value. This one you don't have to memorize.
Yes.
So average value of a function basically takes all the y values and it averages them together. And this is how it does it. So we have to have a function that's integrable on AB. The average value of the function on AB is 1 over b minus a, right? That's the length of the interval, b minus a, times the antiderivative from a to b of f of x dx. So in a very real sense, what it feels like you're doing is like something with like Play-Doh, okay? So imagine over here, I'm going to use this picture since I've already got it drawn on here. Imagine over here you've got this very interesting sort of curved shape, but it's almost triangular, right? And you want that same space, right, that same area, but sometimes it's easier to think about it with volume, but area. And you want to reposition it so that it's now actually a rectangle. Can you imagine using Play-Doh and cutting off the pieces and repositioning them and squishing them in so that it becomes a rectangle? That's what we're doing. And so what we're going to see happen, and I'll draw another picture with the other example in a moment, is that it becomes a rectangle something like this. It needs to be a little bit lower for it to look reasonable. Where it almost looks like this upper piece is being flipped down and filling in this gap, and I've created a rectangle out of the same amount of area. And this height is that average value. So this height right here, the average F value. That's what we're doing, okay? It's not any more difficult. I mean, let's be real. The only difference between what we just did here and what we're about to do here is that on the outside, we're going to multiply by 1 over the length of the interval. That's all we're going to do, okay? But we'll look at an actual version on the calculator so you can see it play out instead of me drawing a picture. So we're going to do this equation. We haven't done a square root yet today, so it seems good that we should do one. And we're going to find the average value on the interval from 4 to 9 of f of x equals square root of x. So again, if you were given this problem, what would I expect to see? I'd expect you to see it set it up. So this is 1 over 9 minus 4. That's the length of my interval. This is the antiderivative from 4 to 9. And it's square root of x, but it might be easier to write it as x to the 1/2. Is set up okay? Great. So most of you did great on finding the antiderivative of things that were square roots on your gateway. What's the antiderivative of x to the 1/2? Over 3/2. And some of you went so far as to even flip this around and tell me that this was 2/3 x to the 3/2. That was beautiful. Well done. You did not need to, by the way. So as you're still working on it, some of you, don't do it if you don't have to. You're just going to make a mistake at some point. No offense. Okay? Good star. All right. So yeah, one of these versions of it. We need to evaluate it. Okay, sorry, I've got all kinds of details left out. So this is 1 over 5 in front. We're evaluating from 9 down to 4. And because there's square roots involved, if you wanted to change it back into square root to do your evaluation, that would be quite reasonable. You can let your calculator do it as well. But it might be that it still has square roots left in the end. This one won't. But let's see, I have 1/5 times 2/3, so this is 2 over 15. And then I have the square root of x cubed, evaluated at 9 and 4. So if I do 2 over 15, which I can multiply by everything, and I have the square root of 9 cubed minus the square root of 4 cubed. Again, your calculator would do this just fine. You don't have to have it written out, but what do you need written out? You need at least to here. All that is a for sure written out statement, okay? So at least that much up has to be done by hand. After that, you could use your calculator for support to get the actual values if you wish. I think we can do this pretty quick. Square root of 9 is, cubed is 27. So I have 2 over 15, 27. Square root of 4, I'm sorry, yeah, square root of 4 is 2, cubed is 8. 27 minus 8 is 19, which doesn't actually have any way to simplify with the 15s in the bottom, so this is simply 38 over 15. But I want you to see what happens in the calculator as I'm sort of trying to justify this idea of, mushing my Play-Doh around. I don't need 2 versions of the calculator for this because it'll do the same on both versions. So go ahead and put that square root of x into your calculator. Oops, I'll put it on the top. I need my window to at least go between 4 and 9. I'm just going to go from 0 to 10. And I'll let my y-axis go from 0 because obviously the square root function needs to be lower than that. Maybe 5 is okay. If you want to do it to 10, it's fine. But this is my screen if I have it from 0 to 10 on x and 0 to 5 on y. It's a pretty good screen to look at it in. So if we want our calculator, and I'm going to do this, I'm going to do second calc, I'm going to do option number 7, and I'm going to do the lower limit is 4, my upper limit is 9, and I'm going to press enter, and it's going to shade that in. Okay, so the shading looks really good. Those of you who have the calculators who are graphing in colors for you, this is going to look even better. But I want you to hit y equals, and that answer that we got for the average value, that 38 over 15, I'd just like for you to put it in, and I'd like for you to graph it. And I know you can't see it running through my graph, unfortunately, but right through here, there's a straight line coming through. And you can see this little part that's above my straight line is filling in this little part over here that's below my straight line, my horizontal line. Do you see that? It's a good idea to graph your average value when you're done. Because if this line had not been through the middle of it, you should have cause for concern to say, wait a minute, I made a calculation error and I need to go back and find it. Okay, it should look visually correct. And if it doesn't, that's a red flag. All right, any questions? Okay, I'm going to leave the video running just so that I can make sure that it catches the announcements, and I'll put the announcements as a post also in Canvas. So anybody who's listening to this in the fall of 2021, this is only for you guys. So a couple things. First of all, we will have a quiz on Monday, right, from 4.3 and 4.4. On Monday as well, we will do 4.5. If we do not quite finish 4.5, I think we will, but if we do not, I'll record a video to finish posting it. I will also be giving you all the review materials for your test next Friday. The reason that I'm going to do that is because I'm going to allow to have one extra opportunity to do the gateway in class, which will be next Wednesday. The reason for that is because on Wednesday, pretty much right after this class, I am leaving town. So you will still have your test on Friday. I won't be here. Another professor will be here to give you your test on Friday. So you'll have your review materials on Monday. If you're done with your gateway, which is about a third of the class at this point, if you're done with your gateway, fabulous, that's fantastic. Those of you who are done with your gateway, you simply, even up to that point, you will not need to come next Wednesday. I would still encourage you, if you are not finished right now, to try to make every effort to come to my office and get it taken care of so you have more opportunities. But Wednesday will be the last opportunity, and it will be in class. Does that make sense? Okay, don't pack up you've already packed up, but don't leave just then, but one more thing. I have an extra credit opportunity for you. Ooh,
What we'd like to
some
hear.
people opened their eyes really big. Okay, extra credit opportunity. It's really easy. In fact, some of you have probably already done it. Did you receive an invitation to evaluate the class?
Yes,
I always think it's funny. If you've done that, you're done.
Oh.
So here's the deal. I don't have any way of seeing who has and hasn't filled out an evaluation. That's because it's anonymous, right? But I can tell how many people in the class, percentage-wise, have done so. That's what I have the capability to see. If we can get to 100% of everybody filling out an evaluation, you all get 3 bonus points. The class is all points-based, so if it helps you to think about it, it's 3 bonus points, just like adding 3 points to a test. Okay, if it helps you to think about it from that way. But it's 3 bonus points. And I totally realize that that's a very communist way of doing this. My hands are tied because I can't tell who's done it and who hasn't. So what you do instead is you turn to your neighbor and you say, have you done it? Have you done it? You've done it? Because I want my extra credits. Okay? So the burden is on you guys to make sure that all of your fellow classmates are participating. In a very real sense, though, and this is true not just for my class, but I know for your other professors as well, but I really use your feedback to make adjustments to my class. I actually used feedback last year to change completely what I did in one of my classes to have, because several people suggested something, and I thought, that has merit. That might be something that would benefit the class, would improve the class in general. And so please give me feedback that you think that would be productive and helpful. That said, if you give me nasty, rude comments, I kind of just throw that out the window as you're not being sincerely, honest and helpful. I really do want your help to make the class better for future classes that I teach of this. Sound good? Awesome. I'll see you guys on Monday.